In previous segments, we have looked at a general technique used in artificial intelligence to solve problems, namely search. We have seen how the efficiency of search can be greatly increased through the use of heuristics. In this segment, we will look at one of the early systems developed in AI for planning, that is the STRIPS planner. One of the advances made by the STRIPS planner was the representation used by it. The STRIPS representation still underlies much of the research done in AI planning today, and the first three parts of this segment will be concerned with the representation. Once we understand the representation, we can see how search algorithms, as we've seen them previously, can be used to solve planning problems. And that is the remainder of this segment. The first thing we will look at now is how states were represented in the STRIPS representation. The way we have looked at search so far is we have treated states as black boxes. That is, we have very limited access to the internal structure of a state or an action. Of course, there are some things we can do with states. For example, we can see whether it is a goal state or not, and this is necessary to terminate the search. We can also find out what the applicable actions are, and this is related to the successor states. Remember, we have defined the successor function to return an empty set if there are no applicable actions. So these two are related to each other and give us information about what can be achieved from this state. More simple functions about states would be an equality test and a hash function. We need those two to turn tree search into graph search. And finally, we've seen how a heuristic estimate gives us some information about a state that we can use to guide the search algorithm. But we had no other access functions to look into the states and actions, so they are black boxes. But our aim in planning is to reason about these states and actions, and that is very difficult if we don't have access to the internal structure. Just think about what we have learned at the end of the last segment, namely that it is possible to automatically derive good heuristics, but this is only possible if we know something about the states and actions in our search problem, so we need to know the internal structure. The STRIPS representation gives us a standardized ways of looking at the internals of states and actions. Now, this is not as pretty as it here shown in the picture, but there will be a formal language that we will define that describes what is going on in a state and what actions do to the state. And that is the fundamentals of the STRIPS representation we will look at now. The STRIPS representation is based on first-order predicate logic. This means we have objects in our domain, and these objects are somehow related to each other. Let's look at our dogworker robot example. In the dogworker robot domain, we have several types of objects that we are looking at. The first type we're looking at are the robots. We will introduce symbols like these, robot 1 and robot 2, to refer to these robots in our logic. So we can use the symbol to denote the robot with the number 1 and the robot with the number 2 and so on. And we can have an arbitrary number of symbols denoting robots. They are of the type robot. That means they all represent a robot. Robots are, of course, the objects that carry container from one location to another adjacent location. The next type of objects we have are cranes, and again we have symbols to denote the different cranes that are in our domain. Cranes can be used to stack or unstack containers from a pile, or load or unload containers onto a robot. As opposed to robots, cranes have a fixed location, so they cannot move. And then we have, of course, containers. Containers are denoted by these symbols here. These can be arbitrary symbols, of course. And they are the things we are moving around in our domain. Containers can be in some pile, or they can be loaded onto a robot, or they can be held by a crane. Robots, cranes, and containers are physical objects. That means they are tangible, and we can see these objects in the real world. The next two types do not have that property. The first one is locations, which denote places that we have in our world. Again, we introduce symbols to represent these different places. These could be a storage area, a dock, a ship, or some parking or passing area in our domain of interest. And then we have piles of containers. Again, we have symbols for these, pile 1, pile 2 here. And a pile can be empty, in which case there is no mass to it, it's not a tangible object, or it contains some containers, in which case we can actually see the pile and the containers that belong to it. Each pile is attached to a single location, so we cannot move the piles around. And at the bottom of each pile we have a pallet. This is denoted by the symbol pallet, and despite the fact that we have several piles and therefore several pallets at the bottom of these piles, we only need one symbol to denote all these pallets, as we don't need to distinguish the different pallets. So, in a state, we have objects, and these objects are grouped into types, as we've seen here, and each individual object is denoted by a unique symbol in our domain. Once we have identified the objects and types that exist in a domain, we need to specify them in a way that a planner can take as input, which means we have to write a text file that defines these objects and types. In this file, we need to adhere to a specific syntax such that the planner will understand what we're trying to say to it. The syntax understood by most planners these days is the PDDL syntax, and PDDL stands for Planning Domain Definition Language. Here is an example of how we can specify a domain in PDDL that defines the types we have just seen in the previous slide. The first thing we do is we tell the system that we're trying to define something. And what we're trying to define is a domain, and this domain has a name. This is an arbitrary name and does not really matter at this stage. But the keywords defined on domain are always there. Next, PDDL allows us to specify requirements for a specific domain. In this case, we specify that our domain requires strips and typing. Strips is actually always assumed, and typing is a very simple extension. But there are many other extensions that you can use. The typing extension is of course required for the types we will see next. The types are introduced by the keyword types, as seen here, and then we simply name the different types, the symbols that identify them. Location, pile, robot, crane, container. These are the types we've seen in the previous slide. PDDL also allows you to insert comments into your input file, and these are introduced by the semicolon symbol. Everything from the semicolon to the end of the line is considered a comment and is therefore not part of the formal language. It will simply be ignored by the planning system. Of course, there's a lot more to planning domains than just the types, and we will look at that next.